I don't get to give academic type talks too often. These are usually the most fun that I have, at least personally. So I'm going to tell you a little bit about why I'm exploring in the Pilbara. I'm going to talk about early Earth and this primordial stew and how it ultimately led to our gold endowment. All right, this slide is one I've put together, collected data over many years, but it basically shows the gold that's been produced by human beings and what time periods that gold originated here on Earth. If you look, the clock starts way back around 3.4 billion years ago. That was in the Archaean, and it takes you all the way up to the present. You can see that a huge amount of gold comes from rocks that are very modern, very young rocks. These are what we see around us every day, in North America, South America, all over the planet. These are basically the most prolific rocks we have at surface. But notice there's a big peak way back there at 2.8 to 3 billion years ago. That peak is actually very important. Notice there's hardly any gold deposits before that. All of a sudden, boom, there was an event that happened on Earth that deposited a huge amount of gold. And most of that gold ended up in the Witwatersrand Basin of South Africa. Currently, about 1.6 to 1.7 billion ounces have been produced from that basin. So you can see that bar outshadows everything else. Wow, that says something. I really want you guys to sit and think for a minute about the importance of that event. There must have been something, we'll call it catastrophic in terms of gold precipitation, but it benefited us in terms of gold endowment, gold that we can mine. All right, so that little purple circle you see there is where that gold originates. That's the Kaapvaal Craton in South Africa. The Witwatersrand Basin sits on top of that craton. All the little pink blobs you see are fragments of Archaean crust, little blocks of Archaean rock. So you start thinking about the importance of that early gold event. Roughly half of the gold originated from, say, 3 billion to 2.6 billion years ago. Yet it's found on crust that amounts to maybe 5-6% of Earth's present exposure at surface. You want to go looking for gold? Go to the Archaean. All right, this little island you see, this was the first continent on Earth. About 3 billion years ago, we speculate there was a continent called Ur. It was a little bigger than the islands of New Zealand, say, combined. But this was the first crust, the first continental crust we had here on Earth. It was a very early time, and that's since broken up. Where did it end up? It ended up in disparate places, all the way from Australia, India, Madagascar, South Africa, even over in Brazil. Little fragments of that have been distributed across the planet. So where do you want to go look for gold? Well, in those little purple dots. India is not such a great location. It's tough to get mineral rights there. South America and Brazil, the moeda is controlled by other mining companies, so that's kind of off limits. Where did I go? The Pilbara in Australia. Now I'm going to talk about why this gold came out of solution. Basically, there was a precipitation event. All right, think about it. The gold had to precipitate for it to become an ore body. And there was a major precipitation event at roughly 3 billion to 2.6 billion years ago. Why did that occur? Well, this chart, somewhat academic, it shows you several elements of geology that occurred over Earth's time. Firstly, the cratonization, this is building continents and stuff, really took off around 3 billion years ago. So there were stable platforms in which we could form ore bodies. But what was even more important was the presence of oxygen. Oxygen emerged as photosynthesis evolved around, we'll call it 2.9 to 3 billion years ago. Yes, there was probably photosynthesis before that, maybe as far back as 3.5 billion years ago, but it really took off around 2.9 to 3 billion years ago. As oxygen came into the atmosphere, gold, which tends to precipitate in the presence of oxygen, came out of solution and formed our present ore bodies. Why did this oxygen come around? Evolution of photosynthesis. Bacteria go as far back as the early Earth history. In other words, they go way, way back to the 3.6, 3.8 billion year range. We see fossil evidence for bacteria. But those early bacteria did not generate oxygen. They lived in reduced environments, really toxic atmospheres that were present at that time. It wasn't until around 2.9 to 3 billion years ago that photosynthesis, or photosynthetic life, bacteria, really started taking off and flourishing. And what you see here is a little section through a biomat, a strata that's usually found in tidal pools and things like this, where you have layers of bacteria. The bottom layers reduced bacteria, but that top layer, that's cyanobacteria, which is photosynthetic and generates oxygen. These things emerged during that critical time period, around 2.9 to 3 billion years ago. So what do I think happened? Well, I put this model together when I was working at Newmont about 15 years ago. I think that seawater back in that time would have been able to dissolve much more gold than it does today. Currently it has about 10 parts per trillion. Back in the Archaean, the Meso-Archaean, perhaps 3 orders of magnitude more gold was dissolved in seawater. As oxygen emerged, as the cyanobacteria took off, that actually caused a lot of the gold to precipitate out. In the case of the Witwatersrand, the carbon leader is actually a fossil preservation of that cyanobacterial mat, and the gold that's precipitated on it now constitutes one of the most important ore bodies on Earth. All right, so let's do a little arm wave here. Gold in seawater. Look, modern seawater has about 4 ppt. I think I said 10 earlier, but somewhere around 4 to 10 parts per trillion. It's actually difficult to measure numbers that small. There's roughly, believe it or not, 20 million tons of gold. Think about that, 20 million tons of gold dissolved in seawater right now. All right, so there's a huge inventory in seawater. Now, think back to the early Archaean. There would have been much, much more gold to work with. All right, so during that time, sulfur-rich atmosphere, methane, all sorts of nasty things in the atmosphere, gold could dissolve at a much higher level. The Witwatersrand Basin underlies about 75,000 square kilometers. I'm going to argue that we can make an assumption the tide, the ocean, crisscrossed that surface, that Witwatersrand Basin, twice a day, way back in Archaean time. And every time it brought in a new influx of gold-rich seawater. And the cyanobacteria mats, they were grabbing that gold as that water was washing across that surface. That caused gold to precipitate out onto the mats, and hence we have these little gold-rich carbon leaders today. But that, just to play with the math, that event didn't take that long. If you look clear down at the bottom, within 2,300 years, so basically in the blink of an eye, you could deposit all the gold that's inventoried in the Witwatersrand Basin through this process. Very conceivable. All right, so these two images show a high stand in sea level when the ocean covered the basin, as well as low stands when ocean level was lower and exposed the carbon leader material to weathering and erosion. So what you end up with in the bits is an original gold depositional event in the form of carbon leader. That's in the upper right. That picture of rock is only about 1 centimeter thick. It's absolutely chock full of gold. That's a fossil coal seam. It's like the first coal seam on Earth. Little tiny guy, but it has an absolute ton of gold in it. It's amazing stuff. When sea level dropped, that material became accessible to erosion and was washed in and became conglomerates. All right, so what we see basically is a struggle between the terrestrial and marine environment, where you were creating gold through precipitation in the marine environment, and then during low stands, the fluvial system, rivers were working across that surface and reconstituting the gold in conglomerates. This diagram shows some detail around that. Okay, so where do we go to look? The Pilbara. So I'm leading into why Novo, why I've chosen the Pilbara to go explore for gold. If we're going to go find something big, we have to look at that critical time period from around 3 to, say, 2.6 billion years ago. I'm going to zoom in and look at a comparison. On the left-hand side, you see a stratigraphic column, or basically a chronologic column of geological events in the Capval Craton in South Africa. On the right-hand side, you can see what happened in the Pilbara Craton. Not all that different. You can see there's some similarities across the board, but it's that critical gold depositional time period that we're focused on. All right, the carbon leader I've highlighted with the star, that carbonaceous material actually formed towards the bottom of the central Rand group which is shown in the middle of the left-hand side. We don't have sedimentary deposition that we know of during that absolute spot-on time period in the Pilbara, but we do have rocks that were deposited slightly before that and certainly after that, and both are gold-bearing. So in other words, we're dealing with a little bit different stratigraphy, but overall, same kind of kettle of fish. This slide was shown by Willem earlier. This is known gold occurrences in the Pilbara at present. We have 3 different styles of gold that we're focused on: Beaton's Creek, Comet Well, Purdy's Reward, and then Egina. Our gold is quite coarse. If you compare our gold to the Witwatersrand Basin, we're dealing with a very coarse gold system. Gold particles that are on the order of centimeters in some cases, as opposed to the very fine gold that you find in the Witwatersrand Basin. Gold in the Wits is often 0.1 millimeter or less. All right, so this is quite coarse gold. It presents its own unique challenges. This, above anything, has been our biggest challenge in exploring the conglomerates of the Pilbara. Think about trying to sample rock that has nuggets like this in it. It's very, very difficult. We've had to learn a lot. It's been painful at times, but we've managed to get a handle on things, and we've brought in some of the brightest minds on the planet to help us. We've now approached this more like one would approach, say, diamond exploration, things like this. So we've employed Simon Dominy, for example, who's a coarse gold expert in the world, who's done some, kind of statistical approach work to help us estimate grades and things like this. And we're finally getting a handle on this extraordinary gold system. I'm going to talk about Beaton's Creek just briefly. This is the first area that we worked in the Pilbara. So we acquired this way back in 2010. Here's the topography at Beaton's, kind of low rolling hills. The stratigraphy is remarkably flat. If you think about these rocks, they're 2.7 odd billion years old, and they are flat as a pancake. They look like they were deposited yesterday. It's remarkable. But the 2 images on the bottom show the examples of the conglomerate horizons that we're dealing with. Some are channelized, in other words, fluvial, terrestrial, and then other conglomerates that we're dealing with were formed in the bottom of the ocean, where you basically had ocean waves working across the surface and concentrating material. So this model shows the kind of the to and fro between ocean and terrestrial environment over time. As sea level rose and fell, it worked across these fans of sedimentary material, producing concentrated lag gravels. Those are our ore bodies at Beaton's Creek. This happened over and over and over again. In fact, we have 7 or 8 cycles at Beaton's Creek that we can demonstrate. What did it produce? It produced these lag horizons. So the photos in the top show a close-up of an outcrop, a close-up of the boulders, and the matrix on the upper right of the conglomerate. The gold is in the matrix, the sandy material between the boulders. These things are about a meter and a half thick. Where they're unoxidized, you can see fresh detrital pyrite. Pyrite is unstable in oxygen atmosphere. So today, if you had pyrite, it'd weather away. But back in the Archaean, pyrite was stable. There's no oxygen in the atmosphere when this was deposited. So we actually have pyritic pebbles in these conglomerates. The upper right-hand photograph, you see the actual paleoalluvial gold component. On the left-hand side, the fine-grained gold component, this is the precipitated kind of gold, is present in the right-hand side of that image. In the bottom there, you see a gold nugget that's actually been folded. So these are truly detrital nuggets that were washed into the basin from older gold deposits. But we also had that precipitation event, which also led to things like carbon. So that little bit of carbon in the lower right, that's a remnant of organic material that was alive when these deposits formed. Very long story short, we've done all sorts of unique exploration techniques at Beaton's, large-scale sampling, bulk sampling, trial mining, yada, yada. But we've come up with the resource. All of this is near surface, albeit a bit, what we'll call underground mine potential. It totals around 900,000 ounces, just over 900,000 ounces now. Weighted average grade's about 2.6 grams for the entire system. It's extensive, it continues at depth. We know the beds keep going in the basin, there's just no question. This will make an excellent mine, in my view. We are now doing an option study to look at how to take Beaton's Creek forward. We expect to have answers around that within a few weeks' time. We're looking at Beaton's Creek in the context of all the other gold deposits in the region as well, just to see what options there might be to work this thing. But it's basically the best gold deposit in the entire East Pilbara camp. Free milling, very good recoveries. So, and the strip ratios are quite low. It's flat, easy to mine. The oxide is all free dig. It's got huge upside. Now I'm going to take you over to Karratha. This is the deposit that was found in 2017. This is the one that stirred up all the excitement a couple of years ago. Purdy's, Reward, and Comet Well. You can see the land position that we amassed based on this discovery. It's an extensive system, but we focus for the most part in that tight little area around the original discovery. Why? Because the gold that was coming out of there and found by prospectors truly gave us an impression that this was a big system, a big conglomerate horizon, never recognized by anyone before. Nobody had mapped conglomerates in this area. Nobody even dreamed that they could exist here. Yet guys were going out with metal detectors and finding gold nuggets by the dozen every day. What have we done? Well, we've done a huge amount of geologic work, very high quality work to put the model together. Here you see a geologic map that we've developed for the Purdy's Reward Comet Well area in excruciating detail. We've diamond drilled for geology, we've bulk sampled for grade. This gives you an impression of cross-section. Through that sequence of rocks, we have two gold horizons, one that sits immediately above the blue, which is the basement, and then another gold horizon about 15 meters or so above that. How did this deposit form, or in what setting did it form? It formed in a near-surface environment, again, where you had sedimentary input from rivers that were carrying a load of gold, and then interaction with the ocean as it rose and fell across the surface. So you basically have this almost natural, Mother Nature's gold pan, if you will, concentrating gold in this nearshore environment. So the two images you see here, the one on the left is actually a transgressive lag horizon at the bottom of the Bering Sea, just offshore from Nome. If you've ever seen the show where the guys are hoovering up gold with a dredge, offshore Nome, that's this system. That is a modern day analog to what we have in the Pilbara. Yes, they do exist, guys. Huge deposits in Namibia. I'll talk more about those in a minute, but for diamonds. Anyway, the gold on the bottom of the seafloor at Nome is the modern day analog of what we found at Comet Well. So on the right-hand side, you see the first nuggets that we found there in situ. As they cracked open the rock, the gold particles were distributed through a lag gravel horizon, just like that one, but 2.74 billion years old. Since then, we've learned a lot about the gold. The gold nuggets that we find at Comet Well have a little halo of precipitated gold. That's actually our precipitation event in the Pilbara. There is a precipitation event. It's manifest as a cloud of fine-grained gold around 2 to 3 millimeters thick, surrounding the gold nuggets in the conglomerates. This photograph shows the nuggets that we find in the lower cannonball conglomerate. These are smaller nuggets. They're maybe 0.x to 1 gram in size. Often, many nuggets within one of our bulk samples. But then when we go up to the upper horizon, we have much bigger nuggets. These nuggets are usually multi-gram nuggets. This is in the upper cannonball conglomerate. The nuggets, although they're bigger, they tend to be less frequent. So the upper unit is about 1 to 2 meters thick. We're seeing grades of about 1.2 to 4.5 grams. And then in the lower unit, it's about 2 to 3 meters thick. It grades about 2.4 to 6 grams. All right, now, interestingly, if you do a gold inventory, say per square kilometer, the amount of gold that we see in these two horizons on a per square kilometer basis is actually comparable to some of the gold endowment in the Witwatersrand Basin. Very interesting. We've looked at mechanical sorting. I bring this up just because this is actually how we're looking at advancing, one of the ways we're looking at advancing this project. And if we go to trial mining phase later this year, we anticipate using ore sorting as a potential means to recover gold. I don't want to digress too much here, though. I'm going to get back on track. Now we're going to talk about our Egina project. This is one that we've put together late last year. It was after we recognized that there's gold-bearing conglomerates in this area, but also there's products derived from those, modern erosional gravels that also bear gold. So at Egina, we have a little bit different story. It's kind of a derivative of the conglomerate story. In the top image, you see this schematic section of what's occurring there. The purple unit that you see on the right-hand side is our gold-bearing conglomerate. And what's happened is in modern time, as that surface has eroded back, that gold has been redistributed down into that red lag gravel, which is basically unconsolidated gravel that's free dig. It's right at surface, easy to access. So we're now chasing what we call the flats, the terrace target. And in the lower left, you'll see what this is. It's flat as West Texas. It's absolutely just flat as a pool table. And there's a gravel horizon that covers much of that surface. And from what we can see, there is a considerable amount of gold in that gravel horizon that was derived from the conglomerates seen in the lower right. All right, so here's a close-up of our lag gravel, free dig. You can plow right through it. It's about 1 meter thick. There's a bit of sand and soil over the top, but otherwise you can mine this stuff straight away. And it's expansive. It covers many, many square kilometers. Conglomerate, we've actually found chunks of conglomerate that have weathered out and tumbled into this lag gravel. That's where our gold is coming from. We found in situ nuggets in pieces of conglomerate in the lag gravel. Very interesting. We did a bulk sample late last year. The bulk sample yielded about 108 grams of gold from about 96 cubic meters of material. You can see the exercise free dig. You just dig it up with an excavator. We have a little test plant out there, so we're able to process these things and get a handle on grade. That's how we're going to move this project forward. It's a very exciting project for us. It has become a shift of our focus because the ease of this thing looks quite intriguing to us. It's not a challenging hard rock thing where we have to send samples off to SGS like we did last year. We're going to do this work this year. Starting in a few weeks' time, we're going to do ground penetrating radar. That'll help us evaluate thickness of gravel and then do a bulk sampling process, a gridded sample sequence after that. Okay, so what I'm going to do today is I'm going to synthesize what we've learned about the Pilbara and the history of gold in the Pilbara region in this critical time period of gold deposition. Okay, so this is really the first time I've ever talked about this publicly. I hope you appreciate it. It's a fairly simplistic model in some respects, but the process of having to think through this and how all these events occurred took a bit of time. All right, so we had to figure out where on earth are all these nuggets coming from. Well, the first gold that was precipitated in the Pilbara Craton actually occurs as orogenic veins. These are lode veins in the greenstones that occur straight the way across the whole Pilbara. There's little gold mines all over the place. Volumetrically, they do not account for very much, though. There's only been a few 100,000 ounces of production out of these gold veins. These were all deposited prior to 3 billion years ago. Subsequent to that, there was a period of sedimentation. This is basically our Witwatersrand, if you will, in some ways, that deposited the gray group as well as some other rock sequences. These are sedimentary rocks that were deposited on top of that granite greenstone basement. Now, what's really interesting is those rocks are enriched in gold. We've done a lot of sampling in Mosquito Creek area, up around Malina, and so forth, where we know that these rocks have a highly elevated concentration of gold within them. It is not carbon leader grade. We have never found a carbon leader, okay? We found bits of carbon at Beaton's Creek, but that's about as close as we get. In the gray group, if I had to speculate, what I would say is this is a bit deeper water part of the setting. So the Witwatersrand was near shore, bay, embayment, some type of deposit like that. This is a bit further offshore. Nonetheless, a huge amount of gold was deposited with these rocks in the gray supergroup. Average gold content of these rocks is on the order of 10 to 20 parts per billion, which doesn't sound like a lot, but that's like 10 times background, or current crustal background. So these rocks had a huge endowment of gold that when then subjected to compression and a subsequent orogenic event. Well, basically orogenic means mountain building, okay? It's a fancy term for mountain building. But there was an orogenic event, compressional event, caused uplift, gave rise to a lot of gold veins. Where did the gold come from? Straight out of the sediments. You have gold-rich sediments, You start squeezing them, heating them, fluids start moving around, and guess what? That gold goes into those cracks, works its way up, and precipitates as low gold deposits. Where the gray group is preserved, around the Pilbara, like at Mosquito Creek, Malina, the Gray's Ground and stuff, there are innumerable little quartz veins, just squillions of them, absolutely. Zillions and zillions of quartz veins. People go out and metal detect these things ad nauseum, all right? They don't amount to huge gold deposits per se, but there is a lot of gold in this sequence. And we know this sequence must have been very thick at one time. But after the orogenic event was complete, around 2.86 billion years ago, everything went quiet for a long time. And all of that crust was eroded down and basically condensed. So all the gold that was in that crust was reconstituted as a lag horizon through a prolonged period of erosion from about 2.75 to 2.86 billion years ago. That's 100 million years time. That's an enormous amount of time to work with. But basically the Pilbara was planed off during that time, probably by oceanic processes. And a lot of the gold that was in all of those rocks was condensed down, and that's the source of the gold that we have at Cometwell and Purdy's Reward. Okay, so this shows you that planing effect, and basically that thin yellow line at the top, that is the lag gold deposit that subsequently became the Cometwell Purdy's Reward type conglomerates. This shows deposition in the Fortescue supergroup on top of the basement. So we have the conglomerates, then we have Mount Roe basalt, the brown is the Hardy Formation, dark green is the Kylena basalts, etc. There's several more units. These were all deposited in the window of about 60 million years back in the Archaean time, between 2.69 and 2.75 billion years ago. So you just stack these rocks straight up on top of one another. All of that gold was preserved, just like at the bottom of a layer cake. It was preserved right on the base, on that surface. We also see an event up into the Hardy. That's the Beaton's Creek event. So the little yellow line that I've drawn there, up in the brown sequence, that's the gold event we have in the Beaton's Creek time, and that does show some of this biogenic activity and other stuff, but I won't go into too much more detail right now. Okay, so subsequent to Fortescue deposition, you deposit a huge pile of sediments, includes iron formations and things like this. These are the rocks they mine the iron ore out of to the south of us, right? That's a Hammersley supergroup. So we had a huge thick pile, maybe several kilometers thick, of material that was deposited on the Pilbara Craton. And then things went quiet. This little piece of crust, for whatever reason, is skittered around the planet with very little interaction with other pieces of crust, very little deformation. You don't see any, big faulting or mountain building, like it's not folded and stuff, not metamorphosed. But in more recent time, erosion has taken those rocks straight back down to that original Archaean unconformity. What has that done? Well, it's exposed this wonderful gold-rich lag surface at the top of the granite greenstone basement once again. All right, so we see the conglomerate now that's at the base, but we also get the derivative of that, which is the Egina gravels, which you can see on the right-hand side of this image. So basically, Mother Nature has cut straight down through the Fortescue group, eroded everything right back to the original unconformity during the Archaean, and exposed this plethora of gold that we have. All right, so this is the first time I've really talked about this model. I hope you appreciate the challenge and thought that's gone into generating it. It's taken some time. We're still learning stuff every day. I'm not going to pretend that we've done detailed academic work. I, at one time, thought I was going to go into academia. Didn't end up doing it. I decided I'd stick to exploration. But I do like to look and think and, understand these kind of processes. I would say that the gold endowment in the Pilbara, one day I hope it proves to be comparable, like what Willem said earlier, to the Witwatersrand Basin. That's my job, to do the hard work. We've got a lot of work planned this year. Is it light speed? Do we go from 0 to 1 billion ounces like that? No, it takes time and it takes a lot of hard work, especially with the nuggety gold, as you can see here. But we feel very confident the system is there. We've got a good handle on how it formed now, and we are aggressively pursuing the areas that we now see as the main focus. So, people say, well, are you abandoning Purdy's reward and comment? Well, no, we are not, but we also now see a high priority at Egina. In other words, look, this story is evolving. I would expect by the end of this year, we'll have maybe 2 or 3 other gold discoveries out of this whole endeavor.